Okay, number 9 from the finals review packet. Here we've moved on to expected value concept from our probability and counting chapter. Here we have a 6-sided die. We're going to roll it. Obviously that's going to come up 1 through 6. And the way we're going to play this, or the scenario we're going to look at here is whatever you roll, you square that number, and that's what you win. So the goal here is to find the expected value of that particular win. And if you recall expected value, we are going to need to build a table like the one I have here. Sorry. Delete that. Delete that. Okay. We have the probability. Here we've listed out the probability for the 6 different outcomes on the die, 1/6, and the probabilities for each one of those, 1/6. We're assuming it's a fair die. And then the payoffs, again, we just take the number and square it, so we have the payoff matrix, or not matrix, but the payoff column of 1, 4, 9, 16, 25, 36. And recall then how to get expected value. What we're going to do is we're going to take each payoff times the probability and then add them all up. So we're going to kind of multiply across here and add them up. So here we're going to have 1/6 times 1, 1/6 times 4, 1/6 times 9, and so on. 1/6 times 36. And then the final step here is we're going to just add all these up. Add them together. And when you do that, you get 91/6. So that was problem, I guess we'll call that problem A. Problem B then is if I change the game so that only an even number is rolled, what's the fair price to play the game? Well, we can use this same payoff matrix, or same approach that we've used here. The probability of the various die, the various faces on the die coming up are, again, all 1/6. But now here we need to change the payoffs. We're saying we're only going to win if an even number is rolled. So here, instead of 1, we're going to change that payoff to a 0. This one's also going to change to a 0. And this one's also going to change to a 0. So if I come off to the right here and add these up, what we're going to have is 1/6 times 0 for the 1, 1/6 times 4, that one's going to stay the same, 1/6 times 0, 1/6 times 16, 1/6 times 0, 1/6 times 36. So again, this is just the same payoff matrix here, except now these 3 have all been zeroed out because we only win the n squared if an even number is rolled. If you go ahead and add those up, you get a number of 28/3. So that would be the expected value of the win in this game. And so here it's asking what's the fair price to play a game. Well, that's what fair price means. It's what you charge someone the exact expected value of the winnings. So the fair price would really just be that same calculation of 28/3. So number 10, this will turn out to be a relatively simple problem in conditional probability. So we have 5 black eggs and 8 white eggs. And then we're going to 3 eggs of each color have a prize in them. And what we're saying is that we did pull an egg with a prize. So we did find a prize. So remember, the notation we want to use here is what's the probability that I found a white egg given that I know I had a prize. That was the notation we used for something like that. I think the simplest way to tackle this problem is really just make a quick little tree diagram. So let's do that. You know, the first thing, if we're picking eggs out of this basket, the first thing that can happen is I could either have picked a black egg, and there's 5 of those, or I could have picked a white egg, and there's 8 of those. And then from there, we have to think about, is there a prize in there or not? So in the black egg scenario, well, we said that 3 of each color have a prize in them. So here we have prize, there's 3, no prize, there's 2. And then on this branch, we have 3 with a prize, and 5 with no prize. Alright, so we have our little tree diagram. And now to solve this, we just need to think about what's happened here. We know we found a prize. So we know that we're living in this sandbox here. Right? So given that we know we had a prize, we're in one of these 6 outcomes. So there's 6 successful outcomes. So if we think about the probability, remember to come back to that fraction idea, 6 total outcomes where there's a prize, and then we want to know what's the probability that we pulled a white egg. Well, when we look at these 6 totals, how many of them came from the white branch? Well, that's going to be this one right here. So the probability of successful outcomes would be 3 white. 1/2. And we're done. So that's the probability of, if I know that I pulled an egg with a prize, the probability that it was white was 1/2. And notice what happened here. The fact that I found a prize gave me some new information. If I didn't know that I found a prize, then the probability of finding a white egg would have been 8 out of 13, because there was 8 total white eggs divided by 13 total. So the fact that I found a prize changed my assessment of the probability to this 1/2 value. Number 11 here is, I guess I would just call this a straightforward plug and chug application of the binomial theorem. Let's remind ourselves what that is. The binomial expansion is if we have a binomial here, a plus b raised to the nth power. In this case, we can expand this out. Actually, I'm just going to put it to the 20th for now. What happens is we get the binomial expansion here. We're going to have, remember, 21 terms. That was one of the things we learned, is when you take the exponent here, you get one more term. And all these terms are going to be of the form this with a coefficient. So the first term, we're going to have a 20th and a 0. And a and b are going to go there. I'll come back to the coefficients in a second. The next term is going to be a to the 19th, b to the 1st. I'll write one more here. A to the 18th, b squared, dot, dot, dot. And then that very last term at the end will be a to the 0, b to the 20th. Notice how these coefficients all add to the exponents of the term add to the original exponent. So 20 plus 0 is 20, 19 plus 1 is 20, 18 plus 2 is 20. And then we also need to now put this coefficient in here. And this was in the combinations chapter. And really what's happening is I'm grabbing these terms, kind of choosing them out of the 20 terms. And so what we saw was that these are all going to be 20c somethings. And then here this is like the number of ways of choosing 0 b's out of the 20 terms in this expansion. So this first term would be 20c0. This one would be 20c1. 20c2, 20c20. Notice how we've just matched up this 0 here with that exponent there, this one with there. Okay, so this was the generic binomial expansion. This is not really the full review here. You can always look it up in your book to get the full deal here. So what we're trying to find is the 6th term. Well, the first thing to notice is that the 6th term is really going to be the term that's going to have a to the 15th, b to the 5th, because the first term here starts with 0, the second term has a 1. So let's just remember that. So when we think about this, we're going to have an a to the 15th, b to the 5th, and we know that the coefficient here is going to be 20c5, again matching this 5 with that exponent. So that's going to be the form of our term. Now we just have to plug in the pieces. We have 20c5. Now a in this case is just going to be 2x. So we'll put 2x to the 15th. And b here is going to be negative y, because we're adding negative y. Negative y to the 5th. And here we could simplify this out a little bit, although this number is going to be really big, so I'm just going to kind of leave it in its unsimplified form. 20C15, if I distribute this 15, we're going to have a 2 to the 15th term, x to the 15th, and do the same thing with this negative 5th here. We're going to, actually I'm going to assume that there's kind of a 1 in there, negative 1 to the 5th, y to the 5th, negative 1 to the 5th is just going to be negative 1. So we're going to have a negative number out in front, and then whatever the value of 20C5 is, times 2 to the 15th, x to the 15th, y to the 5th. So this would be the coefficient of that 6th term. And then our last problem here, number 12, this is our standard inclusion-exclusion principle problem. I'm going to do this problem two ways just to appeal to two different audiences. The first thing I'm going to do is, I'll call it the visual approach. We're going to create a Venn diagram. Remember how we do that? We create the box here, our two intersecting circles. We only have two things we care about here, popcorn and candy. Label that one P, that one C. This will be our universal set of all children. And then we just go ahead and fill in information we know. We know that there's 320 children at the movie. That's going to be our universal set. So I'm going to use this arrow notation to show that the entire box of U is 320 kids. We know that 190 of them are buying popcorn, so I'm going to use that notation to point at the circle here. And then we also know that 245 of them are buying candy. And so from there we can try and fill out the pieces here. We have 151 children by both, so we know that this intersection piece has 151. And then we know that this total circle here of popcorn is 190, the intersection is 151, so we know that that piece here will be 39. So that's 39 who had popcorn but not candy. And then same thing here, we have 245 in this total circle minus 151. That will give us 94. And so from this we can go ahead, and we're trying to find how many children buy neither. So we want to know how many people are kind of in this shaded area here. Well, we know there's 320 in total, and then we just subtract off these pieces that we know. We know that there's 39 who had popcorn but no candy, 151 who had both, and then 94 who had candy but not popcorn. You do that math, you get 36. So I'll call that the Venn diagram method. The other method that you can use here is the inclusion-exclusion principle. And so the first thing we want to figure out is how many people are eating something at the movie. So if you remember that notation, we have the number of elements in P union C. So this is popcorn union candy. So it's really this whole shaded area here. That's the inclusion-exclusion principle says we can find the number of people in the eating popcorn plus the number of people eating candy. But when we do that, we have to subtract the overlap, and so we have to subtract off the intersection. This problem, we can use the numbers more directly here. So we have 190 with popcorn, 245 with candy, and it tells us the intersection is 151. So the number eating something at the movie is 384, and then the number of people, what we really want is the complement of this, people who are eating nothing. So we take 320, the number of people in the universal set minus the number in P union C, and from there we take 320 minus 284, also getting us 36. So here's the algebraic approach, here's the Venn diagram approach, and they agree.